Let's talk about a new way that you can write code so that it's more concise, more expressive, thus making it easier to understand and also to read, not only for yourself, but for others. Plus, it's going to be a really invaluable technique once we start needing to string together multiple commands in order to do some data wrangling or data cleaning on a data frame that you've loaded into R. Now, this new way of coding involves what we refer to as the pipe operator, and we can write this in one of two ways. Originally, it was created so that it was a vertical bar and a greater than sign, but in recent days, it's been changed to the percent greater than percent operator. And we don't have to type that every time. There's going to be a shortcut, the Shift Command M shortcut if you're on a Mac, or the Shift Control M shortcut on a Windows will be very quickly producing that symbol for you with very little effort on your part. Now, at first glance, it's going to make our code look quite a bit different than what you're used to, but you're going to get the hang of it really quickly. Instead of doing something like taking a vector x and running it through the square root function, like what we're used to, sqrt parenthesis x, what we're going to do is something else. We're going to actually take x and pipe it into percent greater than percent into the function that we want to apply to our object, the sqrt with parenthesis. Now, before we explain kind of why this works and why this is going to be so useful, a little bit of history about the pipe operator. So piping has been around in other programming languages for really quite some time, and it came to R about a decade ago in a package named magrittr. Now, that's a terrible pronunciation, and the authors of this package wanted to make sure that this package came off as, a bit sophisticated, maybe a bit pretentious, and it should always be pronounced with some sort of French accent. After all, this package is actually named after the French painter René Magritte, so let's hear how this should actually be said.
How do you say it? For reference in French, this is said as René Magritte.
So I think my bad accent is going to say it as magrittr, but as long as you're not saying something like magrittr, then you should be totally fine. Now, the connection with the artist Magritte is that he has a famous painting of a pipe with the caption, "This is not a pipe," which you may have seen. It's peak surrealism if you're familiar with art history, and he actually has a lot of other pretty cool paintings that you might have seen in books or museums. Paintings such as Apple Face, Lovers, Castle in the Sky, and my personal favorite,
It's raining men. Hallelujah, it's raining men. Amen.
So I guess we could remake Magritte's vision with this new pipe as the following. Kind of a little cute art joke for you there. Now, to understand what piping is all about, let's talk about a few examples completely detached from data and analytics, and let's start by thinking about how I, Professor Petrie, go from waking up in the morning to teaching you in class. The first thing that I do is to wake up, and I'm a pretty sleepy Petrie when that happens. Now, coffee fixes that and wakes me up. Now, once I've had a big cup of coffee, I'm ready to shower, I'm ready to get clean, and I'm going to be ready to face the day. So once I'm clean, I'm going to put on my clothes and then drive to work, drive to the University of Tennessee. Pink Pony Club, I'm going to keep on dancing at the Pink Pony Club. Now, to make this nerdy, we could think of this as me being passed through a sequence of functions. We start out with an object called Sleepy Petrie and run it through a function called Coffee, which we could save to as a new object called Awake Petrie. Now, we take Awake Petrie and then run it through a function called Shower, which has two additional arguments. First, the temperature of the shower, and I would like a hot shower, and a second argument that tells me the length of the shower. I love zoning out, so a nice 15-minute hot shower in the morning sounds absolutely fantastic. Now, we could save the output to an object called Clean Petrie, and now it's time for me to get dressed. So we could run Clean Petrie through a function called Dress, where we might have two additional arguments dictating the color of the shirt that I'm going to wear and my pants. We could save the output of this function to an object called Ready Petrie, and then it's time to drive to campus. So we'd run a function called Drive, where we might have an additional argument that specifies where to drive to, Lot 9 at the University of Tennessee. Now, Professor Petrie is ready to go and ready to teach. Now, we could get really super fancy and nest these commands inside each other so that we could write this in just one big, massive line of code. Now, while this looked pretty slick to have the code on one line, it's nearly unreadable. Now, if you're the only one that ever has to look at your code and you have a perfect memory of all code that you've ever written, this is probably fine. But if you're like me and forget what your code was trying to do an hour or two after you write it, it would take you quite a while to figure out what that line was doing and how it all works. And that's what we're trying to avoid here. Best practices in coding say that our code should be easy to read, which means easy to modify or fix if something goes wrong. Piping is going to allow us to write the code a bit more concisely in a way that's similar to the way you might read or write about functions and operations in natural language, thus making your code more intuitive and easier for others to understand. The same code when piped would look something like this. We start out with Sleepy Petrie and we pipe him into the coffee function. We take that and pipe that into the shower function to get him nice and fresh and clean. And then we pipe that into the dress function to put clothes on him. And then finally pipe that into the drive function to take him to campus. Now, you could actually put this all on one line of code by just having the pipes one after another, but that's kind of defeating the point of what we're trying to do here, trying to make the code as readable as possible. So what really is the pipe doing? What is it accomplishing for us? It's basically saying put what object is to the left of the pipe as the first argument to the function on the right of the pipe. So Sleepy Petrie pipe coffee is essentially the same thing as just running coffee with the first and only argument being Sleepy Petrie. Or if we look at awake Petrie, pipe, shower, hot, 15, that's essentially just the same thing as running the command shower, applied to awake Petrie as the first argument, with hot as the second, and then 15 as the third argument. Essentially, whatever's to the left of the pipe automatically becomes the first argument of the function to the right of it. So one way to think of it is that it's kind of like a relay race where the pipe represents a handoff from one runner to the next. Each runner performs some sort of function to the baton, like progressing its distance a certain amount before handing it off. Or, if you like donuts like me, think about how they're made. We start out with an object like a raw donut and pipe it into a function that fries it. The object that emerges from that, the cooked donut, is then piped into a function that puts icing on it. We could kind of write that as raw donut, pipe fry, pipe frost. We're taking the raw donut, putting it into the fry function, and putting that output into the frost function. And we could write this the old school way as saying frost with fry with raw donut as the argument, but we can see that nesting commands kind of makes it more difficult to read. Now, if donuts aren't your thing, what's wrong with you? You can think of piping in R like baking a cake, another bit of sweets. You take the raw ingredients, you mix them all up, you bake it, decorate it, you slice it, and you serve it, everyone is happy. Now, if we had functions that accomplished all those operations, we could write this as a big old nested mess of functions. We could take mix and apply that to the ingredients to mix up the batter. Put that inside the bake function, put that inside the decorate function, and put that inside the slice function. But I think you'd agree that this nesting makes the code very unreadable. It's hard to know really where to start. How deep do we have to dive into this line of commands to figure out what happens first, then next, etc. Piping is just so much easier. We start out with our object ingredients and we pipe that into the mix function to mix up the batter. We pipe that output into the bake function to bake the cake and pipe that into the decorate function to make it nice and pretty. And then we take that output and finally pipe that into the slice function, slice it up, serve it to everyone, happy crowd, triumph. So when we want to write our code to emphasize a sequence of actions, rather than the object the actions are being performed on, piping is going to be the way to go. When we look at the code taking me from Sleepy Petrie to Professor Petrie, the code really isn't about me or the intermediate me's that are being produced along the way. Rather, it's about the sequence of functions that are applied to me as I get ready. Sleepy Petrie, pipe coffee, pipe shower, pipe dress, pipe drive. It's about this sequence of operations that takes me from waking up to being ready to teach. Now, we'll mostly use piping when doing data wrangling, since in order to get the data into a place where analytics can happen, we have to perform a sequence of actions on the raw data set itself, replacing missing values, subsetting, creating new columns, etc. We won't use it for everything, especially basic functions and commands. You don't need to rewrite all the code you've been writing so far in this piped version because a lot of times it doesn't make sense to do so. Like if we wanted to take the square root of 9, we aren't going to write it like 9 pipe square roots, since just typing out sqrt parenthesis 9 is perfectly readable and would make sense to everybody. Likewise, we won't make a histogram of values, for example, the eruption times of Old Faithful, by running data faithful to load in the data, and then taking faithful $ eruptions, the values in the eruption time column of the faithful dataset, and piping that into the histogram function, with additional argument breaks equals 25 so that we get 25 different bars. Rather, we can just write this the old-fashioned way, where we just say hist faithful $ eruptions. We know automatically what we're actually going to be making the histogram of, comma breaks equals 25 to get 25 bars out. So we're really going to reserve pipes for a sequence of steps applied to one primary object. So let's do some examples. Now, some of these will be designed to show how piping works, even if it's probably not the best way to get the coding done. Otherwise, it'll show you just how much nicer piping can be here. So first off, a basic example where we want to perform a sequence of operations on a vector named spent. So maybe these are 3 different values that describe how 3 different shoppers have spent money at a particular store. So shopper number 1 spent 20 cents. Shopper number 2, $4.3. Shopper 3, $10.1. So specifically, here's what we would like. We would like to take the square root of the log 10 of the values rounded to 2 decimals. That's what I want out of these values. Very often we work with transformations of our original data values instead of the data values themselves. So we do this a lot in analytics. However, one thing that we know is that sometimes when we take the log of a number, the result turns out negative. So if I try to take the square root of a negative number, the result's going to be imaginary, and that's not going to have any real-world correspondence. You know, speaking of imaginary numbers, that reminds me of a bit of a joke. Did you hear about the mathematician that was afraid of negative numbers? Well, after years of therapy, he finally reached the root of the problem, and it turned out it was all just imaginary. All right, you want another? I know you want another one. Did you hear about the mathematician that moonlighted as a carpenter? Yeah, he only worked with natural logs. All right. So if we were to write out this sequence of operations step by step, we'd say spent, left arrow will define that vector of those 3 values. Then we might redefine spent to be the log 10s of the values in the spent vector. And then because we know that those could be negative, we're going to take the absolute values of those. So we'll redefine spent as taking the absolute value of the elements of spent. And then what we'll do is we'll redefine spent by throwing it through the square root function. And then finally, overwrite our definition of spent by rounding the current values to 2 digits. So if we wanted to nest the commands and do it in all one line, we could write this as round square root abs log 10 of spent parenthesis, comma digits equals 2. But this is very unreadable, and you guys have done a lot of coding, and you know that a lot of your time is wasted trying to figure out where the parentheses match, where the commas need to be, and this is just a difficult way to actually write the code. It's very, very messy.
What'd you do? What did you do? Oh, what did you do?
So instead, what we can do is we can apply piping. So we can start with spent and pipe it into the log10 function. Spent pipe log10, and we don't need to have any actually arguments in the log10 function since the pipe automatically places what's to the left of it, the object spent in this case, as the first argument. So spent pipe log10 is really the same thing as just log10 parenthesis spent. Then, once the log has happened, we can pipe that into the absolute value function. This also doesn't need any arguments since the pipe automatically places what's to the left of it, the log 10s of spent, as the first argument of the function. So we've got spent, pipe log 10, pipe absolute value, and once the absolute values happen, then we can pipe that into the square root function. So spent, pipe log 10, pipe abs, pipe square root, and pipe that into the round function to take us to completion. So once we pipe that into round and then parenthesis digits equals 2, we're going to be done. Now, normally we write round as round parenthesis vector comma digits equals 2 in order to round to 2 decimal places. But since the pipe automatically places what's to the left of it as the first argument of the function, we just need round digits equals 2 on the right-hand side of the pipe. So, voila, 2 ways of performing the computation, but I think you'll agree that using pipes makes it a lot more readable. Looking at the line of code, it kind of reads like a story. You take spent, then log tenant, then absolute value it, etc., etc. To read that first line, you have to dive deep into the mess of functions to figure out what needs to be evaluated first, then work your way or break out of the parentheses one set at a time. And that takes a little bit of skill to figure out where do you actually start, what's next, what's after that, etc., etc. Piping's the way to go. So another example. Let's imagine that we have a vector of the total number of items that 100 different customers have purchased in their shopping cart. Some customers will just have a few items, others will have many, and let's generate these values at random just for illustration. So we'll set the random number seed and then define an object called orders to contain these values for 100 different customers. Now, here's my question. I would like to know what are the 4 smallest unique values in the vector. Now, we can kind of identify this visually just by running the command sort orders, which is going to output the values of orders from smallest up to biggest. And if I just scan through, I can see that the 4 smallest unique values are 4, 7, 8, and 10. But I need to figure out how to get R to automatically figure this out for me. So let's try to do this by coming up with a story or a sequence of operations that we need to perform on the orders object that we have to tell in order to get the answer. So what do we really need to do? Well, step 1, what we should do is strip out all the duplicates, essentially keep only the unique values. Step 2 would be to sort them from small to large, and then step 3, print out the first 4. That'll give us the 4 smallest unique values. So let's go ahead and set up the pipeline. First, what we're going to do is we're going to take orders and pipe it into the unique function, and that's going to strip out any duplicates. So when we do orders pipe unique, what we see is that the output, there's no duplicate values. You might have to take my word for it here. I can't really tell by just looking at it, but that's what the unique function is really doing. And then what we can do is we can pipe that into the sort function to sort from smallest to biggest. And then what we can do is we can pipe that into the head function to get the first 4 values. And once we do that, we have R automatically telling us that, okay, the 4 smallest unique values in the data are 4, 7, 8, and 10. Now, you might remember that normally we run the head function by having the first argument be the vector and having the second argument be the number of elements that we want to see. For example, head parenthesis x comma 4. But remember, the pipe automatically places what's to the left of it as the first argument of the function. So the sorted vector of unique values is what we're taking the head of. We only need head parenthesis 4 because the pipe is automatically putting in that first argument as the vector that we want to work with. Now, this line of code is pretty readable on just one line, but what we can always do is to split up onto multiple. It never hurts to split up code just for the sake of clarity. So we'd have orders pipe, then new line unique, pipe new line sort, pipe new line head 4, so that we know exactly what step is one after the other, what's happening to our orders vector as we're going towards our answer. So much better than if we had tried to write it the outdated way, kind of nesting the commands, doing head, sort, unique, orders, parenthesis, parenthesis, comma 4. Good luck matching those parentheses, getting the commas in the right place. That code is really just the mess. And that's really my favorite part. I think it's the best part. You never have to worry about matching up parentheses with these nested commands if we just write it as a sequence of pipes. Now, one last example before we conclude, and this will look a little bit to where we're going with data wrangling with the tidyverse and dplyr. So some of these commands may not look familiar just yet, but I think you'll still be able to follow them. So let me load up the cust loyalty dataset in the reg class package, which keeps track of the lifetime values of 500 customers to a store, whether they're single or married, their gender, etc. So loading up library reg class and then loading in the data with the data command, we can look at the first few rows of the data frame. We can take cust loyalty and pipe that into the head function, maybe look at the first 5 rows, and so we can see what we're dealing with. So I have a question. What I want is a frequency table of the loyalty card statuses of the 8 single female customers that have the largest lifetime values. So I've got to figure out a way to get R to extract out just the set of customers that I want to be looking at, and then also look at specifically the 8 ones that I'm the most interested in. So we could do this the old school way in steps, defining some intermediate objects along the way. So step 1 would be to get the subset of single females. So we'd run the subset command, a base R command, using the cust loyalty data frame and just extracting those rows where we have gender being equal to the word female and married equal to the word single. If I were to run this and define an intermediate data frame sub for subset, I could get a summary of my subset just to verify that, yes, I've done what I wanted to. We only have females, single females here. Step 2 would be to say, okay, we'll take our subset and let's sort the rows based on the values of the customer lifetime from smallest up to biggest. And sorting in base R is kind of obnoxiously difficult and counterintuitive. What we do is we reorder the rows. So how do we do that? Well, right after the sub data frame name, we slap some square brackets, and inside the square brackets, we put a comma. And if you remember, before the comma, that's our row references. After the comma is where we refer to the columns. We'll leave that blank because we want all the columns. And what we'll do is we'll give the rows a new ordering by running the order function. Order essentially is going to let you know, okay, as I dive in through each one of those lifetime values, is it the smallest, the second smallest, the 143rd smallest, etc.? So when I reorder these rows with the order command, and we can just look at the first few rows of sub, we can verify that indeed it's being sorted from smallest lifetime value, getting larger and larger and larger. So once we have that, actually, we could look, let's say, at the last 8 rows of our data frame. So these are the 8 largest customer lifetime values. And if we go and look at the loyalty card status, we see, okay, there are 6 people with loyalty cards and 2 people without. So the majority have loyalty cards. That's good news. So we could make R do that by just running a frequency table on the last 8 entries of the loyalty card column, tail sub $ loyalty card, comma 8, and this would give us basically the answer immediately. So technically a functional but completely unreadable line of code that gets this all in one step would look something like this, kind of writing the table command applied to the tail of taking our subset where we reordered the rows in cust loyalty by customer lifetime value, where the rows have female gender and single marital status, but this is a gargantuan mess. Would we ever actually do this? Well, we could ask the kids from Saved by the Bell, that classic 90s sitcom.
Dumb.
Stupid.
Crazy. Dangerous.
So this is absolutely terrible, but by using piping, it's phenomenally easy. And actually using some functions from the tidyverse and dplyr are really going to help us out with this data wrangling to answer questions like this. So let's use piping instead, since we're doing a sequence of operations on a single object, the cust loyalty data frame. How would we do this? Well, we start out with our cust loyalty data frame, and the first thing we're going to do is we're going to pipe it into our subset function. Now, we'll use the filter function to take our subset, so we essentially say, well, what rows do we want to keep? We want to have the rows where gender is equal to female and married is equal to single. So cust loyalty pipe, that filter is going to take our subset, and we can take that output and pipe that into the arrange function. The arrange function does the sorting for us. It says, okay, what do you want to sort by? In this case, customer lifetime value. So piping the filter output into arrange is going to reorder those rows so that they're ordered from smallest lifetime value up to largest lifetime value. And then what we can do is we could go ahead and get the last 8 rows. We could pipe that into tail 8 and then get a table of the values in the loyalty card column. So we can pipe that into the select function, which just isolates a particular column or columns that we find interesting, and pipe that into the table function. So why does this work? Start with our data frame, take the subset of just single females, reorder those rows, get the last 8 rows, just look at the loyalty card column, and get a frequency table. And once we do this, we get the same answer. But this is a much more readable story. Everyone can understand what's happening. It'd be easy to modify. So we're pretty much good to go. And so there you have it. In order to make analytics happen, we always have to get the data cleaned. Since this usually involves a sequence of operations applied to the data, piping will make this a lot easier to read and to fix if anything goes wrong. You'll still be writing plenty of commands the standard old-fashioned way, so don't forget about that. For instance, if we wanted to make a scatter plot of the relationship between the customer lifetime value and the wallet share of these customers, we're still going to invoke the plot command. Plot customer LV, twiddle wallet share, data equals cust loyalty will make us a nice scatter plot. And if we wanted to do some regression modeling, maybe predicting customer lifetime value from wallet share, we'll still use the LM command, like what you're familiar with, and have our formula be, say, customer LV. Let's do twiddle dot. Let's actually predict customer lifetime value from every single one of the predictor variables that we have accessible in the data. And then once the model's been created, we can just get a summary of it directly with summary and in parentheses, model the object that was created by the LM. But of course, you always do have options. You can rewrite code a different way. You could actually rewrite the code fitting that linear regression, then getting a summary of it by actually just writing out the LM command, fitting that regression, then piping it into the summary command. Because you know how pipes work. What it's going to do is it's going to take the output of what's to the left of the pipe and automatically put that as the first argument of the function to the right of the pipe. So it's going to get a summary of the model that's just been fit. So new power unlocked. I think you've leveled up and you're becoming the next best, greatest analytics practitioner. Way to go.